All right, question 3 on the AQA AS 2019 paper 1 as a review for a mock paper, or of a mock paper. So we've got a reverse bungee. Okay, in other words, it is something that shoots you up into the air and then pulls you back down, as opposed to jumping up and being pulled back up, or jumping down and being pulled back up. So here we've got two identical stretched ropes with a cage with the passengers inside. Alright, some more information about it. Okay, and all of our measurements seem to be just center of mass. So we have tension of 3.7 times 10 to the 4 newtons, an angle of 20 degrees with the tower, and the mass of the loaded cage is 1.2 times 10 to the 3 kilograms. And the ropes have negligible mass. Show that the downward force exerted by the clamp on the loaded cage is about 6 times 10 to the 4 newtons. Okay. Well, let me draw my little triangle here. Oops. Okay, so I will have an upwards force here and a force to the side here. So if that's my theta, this is going to be F cos theta. Is this or T cos theta? Let's call it T because it's tension. So if I look here, I'm going to have two T cos thetas going up. So I'm going to have 2 T cos theta is going to be equal to my reaction force, which is the clamp pulling down, but I've also got weight. So, a couple of places that we could easily have made a mistake. One, forgetting to double our the tension because there's two ropes. Using sine instead of cos theta, and forgetting the fact that there is a weight. Okay, so the force that we want is going to be equal to 2t cos theta minus, oops, not equals, minus m times g. So 2 times 3.7 times cosine of 20 minus 1.2 times 10 to the 3 times 9.81. Alright, mathing it out. 2 times 3.7 times cosine 20. I have made a mistake in writing something down because that is definitely not right. It should be 10 to the 4. That makes a big difference. So don't make the blunder that I made. There we go, which is equal to 5.9 times 10 to the 4, which approximately equals 6 times 10 to the 4. Remember, for a show that question, you must show your answer to at least one extra significant figure versus what they have you showing. There's no point in just writing all this down and then going, yeah, so that's about equal to 6. You actually have to show your workings out. So calculate the initial acceleration of the loaded cage when the clamp is released. Well, F equals ma, but the force in this case is going to be equal to, the reaction force, really, 5.9 times 10 to the 4, because all of a sudden that reaction force is not going to be there. It's going to be unbalanced by that much when the clamp is released. So acceleration is force over mass. And we've got 5.9 times 10 to the 4 divided by 1.2 times 10 to the 3. Okay. Equals 49 meters per second. Meters per second squared. Okay, it might round to 50 depending on if I just had the number sort of saved in my calculator. But that's the right method for it there. So the unstretched length of the elastic rope is 24 meters. The rope obeys Hooke's law for all extensions in the ride. The vertical distance between points P and Q is 35 meters. Show that the elastic potential energy stored in both the ropes before the loaded cage is 5 times 10 to the 5 joules. So first things first, the length of the rope when it is stretched. Well, again, a little bit of trig. Okay, so if this is 35, then we have to divide by cosine 20. So 37.25 meters. And that means that our delta L is equal to 37.25 minus the unstretched length, 24, 13.25 meters. Okay. And we just want to make sure we use the right formula for potential energy. Okay. So elastic energy is right, 1/2 no, it's just 4 1/2 of force times extension. Okay, don't forget the 1/2. is 3.9 times 10 to the 5. I've made a mistake somewhere here. Where have I made my mistake? Now, obviously, I've got a problem. Right. I made a very big mistake, and the big mistake was in my force. Okay, I used the wrong force. I used the force from the clamp, and obviously I've got to use the force that each rope has, which is the tension in the rope, which is 3.7 times 10 to the 4. That was stupid of me. And, oh, hey, there's 2 of them. So let's multiply it by 2. Because I'm multiplying by 2, I don't need that. Then there we go. Now it's 4.9 times 10 to the 5. Which approximately equals 5 times 10 to the 5 joules. So you can see, if you are trying to go too fast and you're not really paying attention, you can easily make mistakes. Fortunately, this was on a show that question, so I could see that I wasn't showing that. So I could recognize that my answer was, in fact, wrong. Okay. So the designers of this ride claim that the loaded cage will reach a height of 50 meters above Q. Deduce whether this claim is valid. So we have a potential energy of 5 times 10 to the 5 joules, 4.9 times 10 to the 5 joules. So let's take a look. If all of that energy gets turned into gravitational potential energy, well, mgh, so 4.9 times 10 to the 5 is equal to, let's not make some mistakes again, 1.2 times 10 to the 3. Times 9.81 times h. So h is equal to 9.81, and it's only going to reach a height of 41.6 meters. So it's not justified. Alright, so the designers here have claimed that the loaded cage reaches a maximum speed of at least 90 kilometers per hour. So, calculate the kinetic energy if it's traveling 90 kilometers per hour. Okay. One half mv squared So 1/2 times 1.2 times 10 to the 3. Now V, we don't want to use kilometers per hour here. If you do, you will get the wrong answer. So we have to convert to meters per second. So you divide by 3.6 to get to meters per second. We square that, and why does everything have a 9 in it today? So 3.75 times 10, well, 3.8 times 10 to the 5. Okay, so without further calculations, is it possible? Yes. Because the EK is less than the elastic energy. So it's possible. We don't know if it's 100% true or not, though. We just know that it is within the realm of possibility. All right, that's question 3 done. And you can see, even I make mistakes.